So, we will look at the term 1, the first term we will look at it, and the first term can be expressed as CMT1. These two terms, we will see that these two terms cannot be satisfied simultaneously. One of the terms will be satisfied at a time. So, that is why we are looking at each term separately. So, I have this C1 M this coefficient term. So, I started with n state and my final state is m state, but I really do not know yet whether the final state has to be higher in energy or lower in energy. That we do not know yet. We will just prove it right now what is going to happen. Both transition are possible and each term is corresponding to one type of transition. So, first this term we will look at it, and if we write it down, then it is going to be minus E by m A naught by 2, then special integration e to the power minus I k naught dot r k naught dot r, then epsilon unit vector, then this derivative operator, and then this is the special integration I have. Then I have this T1 term and e to the power I omega mn plus omega naught t 1 by 2 term, and then cardinal sine function term, which is omega mn plus omega naught then T1 by 2, this term I have. And the probability of transition is probability of transition from n state to final m state is at time t1, this at time t1. So, once I have turned off the interaction process, I am just trying to find out immediately after the interaction process has been turned off, what is the final population, and the population in the final state is corresponding to the probability of transition. So, that population I will call it, let us say that population will be given by absolute square of absolute value of this term. And if we take the square of absolute value of this term, what we get immediately, I get E square m square A naught square divided by 4. On the other hand, this one is going to be now absolute square of this term, then T1 square, then this part will be gone because it will be multiplied by its complex conjugate. So, any complex quantity will be gone, and then this is going to be square of this cardinal sine function, and square of the cardinal sine functions is plotted here. So, previously I plotted the cardinal sine function itself, it was like this oscillation, but because I am squaring it there will be no negative values. So, it is going to be all positive values, and we are getting it. What we have shown here, it is taking maximum value at the 0 variable equals 0. So, this is the variable right now, and it takes the 0 value at when it is pi. So, what we see here is that this cardinal sine function, this will be negligible, it will make the population negligible unless we have Wmn equivalent to minus omega naught. It has to be minus omega naught because the entire term has to be close to 0, and if the entire term has to be close to 0, then omega mn has to be minus of omega naught. Or in other words, we know that omega mn, what does it mean by omega mn? It is actually Em omega mn has been defined as previously we have defined omega mn, and that was Em, the difference between the energies, and that if we employ that, then I can get this Em equals En minus omega naught h cut, because this omega mn is going to be omega mn is Em minus En divided by h cut. So this is going to be now minus omega naught. So I get the maximum population when this term becomes 0, because this has to be 0, and if I have this term to be 0, then omega mn has to be like this. So Em has to be En minus omega naught h cut. It shows that Em energy has to be less than En, and the initial state of the atom, the initial state of the atom, this shows that the initial state. So if it is deviating too much from 0, this entire term, then the cardinal sign function will become 0. It has to be very close to 0, this entire term, then only I get the maximum population. So which suggests that the initial state must be greater initial state energy must be greater than final state energy, which means that one photon in this process. So I have a situation where initial state energy is greater than final state energy, and atom will be making this transition. If the atom is making this transition, then one photon has to be emitted, that is omega naught h cut. That one photon has to be emitted. One photon must be emitted. One photon must be emitted. This process is called stimulated emission. So what we are seeing here, the first term which we have got, it is indicating a behavior of a stimulated emission, and stimulated emission is possible only when the this cardinal sign function, this entire term within this cardinal sign function, that term has to be very close to 0, and if we consider 0, it means that the one photon will be emitted. Let's look at the second term. The second term is going to be here, and we can again write down. So we can directly write down Cm T1 population, because square of absolute value of this Cm, this coefficient, is related to the population in the emit state after the interaction has been turned off. So that is going to be now E square by m square, then A naught square by 4, then I have this absolute square of this this integration e to the power I k naught dot r epsilon dot this integration, then T1 square, then this part is actually complex part. So when you take the absolute value, square of absolute value, we multiply by its complex conjugate, so that part cancels out, and so finally I get cardinal sign function square of w omega mn minus omega naught T1 by 2, the square of this term. So again the same argument is valid. This value has to be very close to 0. If it is deviating little bit, then the cardinal sign function is 0, and if it is 0, then population will be 0. So, there will not be no population in the final state. So, in order to have the population in the final state, this is the initial state, and in order to have a population in the final state, this has to be 0, and if it is 0 or close to 0, then omega mn has to be close to omega naught, and if it is so, then I will be able to write down Em equals En plus h cut omega naught. This shows that the final state energy, this is m state energy, is higher than this. So, the final state energy is greater than the initial state energy. So, previously we have seen the initial state energy was greater than the final state energy. Now, this time we are seeing the final state energy is greater than the initial state energy, and as a result, one photon, which is h cut omega naught, is absorbed from radiation. So, always in both scenarios, previously also there is an interaction of light and atom. During this interaction, due to that interaction, there will be new photon which will be emitted. That is why it is called stimulated emission. This stimulated emission is different from spontaneous emissions. For spontaneous emission, I do not need any interaction of light and atom. Even if you turn off the radiation, the system which is electronically excited or vibrational, they will spontaneously come back to the lower energy state. That is called by emitting photon. That is called spontaneous emission. For stimulated emission, I need interaction of the atom and light, and due to this interaction, another photon can be emitted. That is called stimulated emission. Here, due to the interaction, because this entire term comes from the interaction term. So, due to interaction of atom with light, we have now a photon absorbed from the radiation, and the photon amount is h cut omega naught. That is why this is called the absorption process. It is clear from here that there are only two terms I am getting from first order perturbation theory, and that we have mentioned before. One of them is showing stimulated emission, another one is showing absorption process, but this treatment directly does not show the possibility of spontaneous emission, and that we have already mentioned that the semi-classical treatment does not include the spontaneous emission directly. We have to use statistical argument to get the spontaneous emission, the picture of spontaneous emission from semi-classical treatment. So, we have come to the end of this module. In this module, we have discussed how an atom can interact with light with the help of first order time dependent perturbation theory, and we have made use of this vector potential which is created by the light when it is interacting with the atom. So, atom when it is interacting with light, it is actually interacting with the vector potential of the light, and we have seen that semi-classical treatment directly gives me two terms finally. Those two terms indicating that spontaneous emission is possible, not spontaneous, stimulated emission is possible and absorption is possible, but it does not show any term directly for the spontaneous emission. For the treatment of spontaneous emission, we have to use statistical argument. So, we will stop here, we will meet again for the next module.